Hey everyone. Today we're going to start off with a little bit of practice with compound and continuous interest, and then hop into kind of the main lesson, which is on determining growth rate of an exponential function. So here what I would say for this kind of first piece is twofold. One, I don't need this to kind of be collected, graded for accuracy, so you can kind of cross out this points line. And then there's 4 problems here where you are practicing with the equations up top that we learned about in class. I do encourage you to kind of go through those, but I won't be collecting it. So just kind of be mindful. I do think that practice is going to be a good idea, especially just because in class I think there were still kind of some questions that were had on this topic, so definitely worth taking a look at. And then on Friday, for you folks, the gray pack, there is going to be an assessment. So, if I try to get that date, one sec. So October 30th, an assessment for exponential functions we will be reviewing in class, and potentially even a part of Wednesday, although I haven't really decided what that Zoom day looks like. So just kind of be mindful of that, reviewing in class and then test on Friday. So looking at kind of our notes for the day, we have this fact that all exponentials can be written in this one form here. So, and this is kind of important because it means that we can write any exponential using e as our kind of base, regardless of the context. So even in this situation where we had tennis players being eliminated, anything in those contexts, we can actually just all use the exact same exponential equation that looks like this form. And I'm going to show you how to do it. The thing that's going to be changing basically is this r value that we have in our exponent. So a lot of our goal today is going to be trying to figure out what that r value is. And this gets to the point of, with linear, we learned about, or linear or quadratic, you learn about all the equations, the forms, and everything like that. But eventually you get to this point where really you just want to be given a real-world problem situation and then writing, a difficult exponential equation or a difficult quadratic. So this is what we're going to attempt to do here. So suppose an investment grew from $10,000 to $20,000 over the span of 20 years. So the pieces of this that we know in this particular equation, we know how much we started with, we know how much we ended with, and then we know the amount of time that it took. So I'm going to put these as my variables here. Okay, so, and I'm grabbing those variables right from above. So I have A, P, R, and T to try to figure out, and I was only able to figure out P, the principal, A, the amount that we have left, and then T. So I don't know R. And reminder, E is not a variable. E is this number, 2.718, and then it kind of keeps going out. If you want to know what it is, you can type e to the first power on your calculator. So if I plug these components that I do know into this expression, so I'm going to say 20,000 equals 10,000 e to the r, and then basically times 20, or I could have said to the 20r. So those are all the components that I can put in there, and now if I try solving this for r, I will have kind of created the exponential equation that would have got us here. So first I'm going to start by dividing both sides by 10,000. And what you'll generally find here is that we get down to like a nice easy number that basically that 2 is really just telling us that we doubled. And then on this side, I'm going to say we have e to the 20r. So here we can convert this right now to an exponential, a logarithmic equation if we wanted to. How I'm going to be showing this, and I believe we talked about it in class, is we're going to take a solving step in order to kind of get this ship righted at this point, or to solve this. So if I have this, something like this, what I've been recommending, we start thinking about is, okay, take log base 3 of both sides then. So we take log base 3 of both sides. And when I take the log base 3 of this right-hand side, I'm just going to be left with x, and when I take the log base 3 of the left-hand side, that's something I can then just plug into my calculator. So similarly here, for folks that remember, this e is our special one, so we actually have a special logarithm that we can kind of take here. So if I take the natural log of both sides, on the left I'm going to end up with the natural log of 2, and when I take, I'll write it all out here, but this is the natural log of e to the 20r. This is just going to end up giving me 20r. Okay, and I haven't solved for r, but I'm also not going to evaluate what the natural log of 2 is, because it's really accurate right now, and as soon as I put a decimal to it, it's just going to be less accurate. So this is just going to be a rewrite, just so that I'm a little bit more clear about my solving step, and then I'm going to divide both sides by 20. So r is going to be the natural log of 2 divided by 20, and now I'll plug that into my calculator to get an approximation for it. So I'm going to end up getting 0.0346. And I might go out to like 4 decimals here, because we're going to be expecting decimals pretty frequently. So now that I know my r value, if I want to create a modeling equation for this, I'm going to leave a out of it. That was kind of the amount that we ended on. And I'm only going to take my p value. Let's say that this is going to be 10,000 e. This is going to become 0.0346 t. So notice what I've left as variables are really, they're kind of like x and y basically. So I left a as a variable and t as a variable here, because now I have an equation where if somebody told me a point in time, then I can go and figure out another amount that our investment has grown to. So first I know that if I plug 20 in here, that I'm going to get 20,000 out, because that's basically what I solved for here. But I can also now use this to say, well, okay, what would they have after 40 years or after 30 years? So this is kind of a newer process for figuring out what that r value is in this specific format. All right, so let's take another look. We have a equals pe to the rt. A equals PE to the RT is the format that we're trying to get all of these exponentials into. Population of Colchester can be found. So here we've got basically a census between 2 different years, and we're trying to figure out what the population is going to be. So here, let's say this would be my P value, kind of my starting value. This is my A value. Okay, because my population changed from that to that, very similar to my investment. And then my t value here, I'm going to say is 10. And what I can kind of say is my equation, t is time since 1960. So I don't want to lose sight of that or lose track of that. Okay. So let's plug everything I know into my equation. So I know 8,776 equals 4,718 e to the, I'm going to say 10r. It is r times t, but I didn't want to write r times 10. I just wanted to be here. And then my solving steps should be pretty much the same throughout a lot of these. So here I'm going to divide both sides by 4,718. Plug that into my calculator, 8776. So I'm getting 1.86. I'm going to leave it at that. The next decimal is going to be a 0. Here I just have e to the 10r. I can convert this to logarithm form if that's kind of what we're comfortable with. But again, I'm going to show us that in order to get rid of that e, or to bring down that exponent here, I'm going to take the natural log of both sides. So this is natural log of 1.86, and when I take the natural log of this side, I'm just going to be left with 10r. Finally, to get r by itself, divide both sides by 10. So I have natural log of my answer. Let's do 1.86 divided by 10. So I'm getting r is 0.062. And that is what I'm going to plug in. My next decimal is 0 there. That's why I didn't go out to 4. So my equation here that I can write, and once I know this, again, I'm only going to plug back in basically my initial principal. So this is E, and then 0.062 T. All right, so that is my modeling equation. So now notice kind of at the end of this, it says, what is the predicted population in 2020? So for 2020, I'm okay to do this here. I don't need to go changing any dates like I did in the previous assignment. Here, what this means is that T equals 60. So it wants us to plug 60 into this equation because we are 60 years away from 1960. So now I'm going to just plug that into my modeling equation. And we'll see what we get. So 4718 e to the 0.062 so 194,685.41 is kind of the predicted population if I use these two data points here from 1960 to 1970. Seems like there was a lot of growth between 1960 and 1970, so that probably obviously didn't hold true on into the future. Here we're going to kind of do the same process. You're going to look at some, two starting points, figure out basically that we have our P, A, distance between these, basically referencing what our time is. Then we can create that basic equation of A equals PE to the RT, plugging what we know. Then you're going to end up solving for R, and then you rewrite your model equation. Because that time all you're going to plug in is basically P and R. All right, so see how this goes. This is going to be kind of a little bit tricky, but I'll also see if I can do a few more examples here and upload those kind of semi-completed notes onto your calendar as well. All right, good luck.